Hello, everyone, and welcome to our last video on linear transformations, or transformations of functions. There we go. I slipped up. So now, what if we're going to try and graph a transformation that has more than just one thing? So, step one is to create your function's equation by following each transformation. Sometimes problems will tell you the transformations they want you to do. Other times they'll give you the equation, and we'll get to those ones. Then step two is to draw a small parent function for reference. Now, if you're like, this can be done in the head. If you're really, really good about it, or you can print off the first 2 pages of this worksheet that you filled out and utilize those to have a parent function graph in front of you. The reason why I want you to do that is so that you can watch what happens. You can trace along and see what happens to each point. Then on the big graph, the actual problem in hand, using your mini graph, you're going to use your pen or pencil to carry out the transformations in the order given. On each important point of the parent graph, and upon performing the last transformation, jot down the location. I recommend jotting it down and not plotting it until you've got all your points, because otherwise things can get really, really messy very quickly. It's not required, but I do recommend it. And last but not least, once you've jotted down those points, plot them, plot the points, and graph. So, for example, find the equation of the function that is graphed by following the transformations to the graph of f of x equals x squared, and then graph said transformation. So you've got to transform it by shifting it up 2 units and then right 1 unit. So first we start with f of x we'll start with x squared. Let's just write x squared. The first transformation, that is a shift up 2 units. So that's a vertical thing. That's a shift up. That's a vertical shift. That happens on the outside based on our pro tip from up above. Vertical stuff happens on the outside. So this should be x squared plus 2. And then our second transformation is to shift right 1 unit. That's a horizontal thing that happens on the inside of the function. And since it's right 1 unit, you would think that it'd be going you'd think you'd be adding 1, but you're actually going to be subtracting 1, because horizontal stuff acts opposite of what you would think. So this is now going to be y equals shift right 1, that'll be x minus 1. So we're going to subtract 1 on the inside, and don't forget about your plus 2. So that's our function's equation. Now the parent graph, x squared, that's got the points 0, 0, 1, 1, and negative 1, comma, negative 1, or negative 1, comma, positive 1. And it looks like that. And so this is what I mean by step 3. So let's start with the point 1, 1. So I'll start at 1, 1. First, I'm going to shift up 2 units. 1, 2. Then I'm going to shift right 1 unit. 1 unit right there to the point 2, comma, 3. I'm going to jot that point down. 2, comma, 3. I'm not going to play. It won't bother me this time, but it can cause issues late, like if the points are all clustered really close together. But once again, it's not required. If you want to just plot it right off the bat, that's fine. Next, we'll talk about 0, 0. First, 0, 0 gets shifted up 2 units, 1, 2, then right 1 unit to 1, comma, 2. And last but not least, the point negative 1, comma, positive 1 goes up 2 units, 1, 2, and then over 1 unit to 0, comma, 3. The other reason is if you have to plot points, now you don't have to like do it in your head. You've already jotted them down, so you're done. So now we'll plot them. So 2, comma, 3 is right there. 1, comma, 2 is right there. And 0, comma, 3 is right there. And that will be our transformed graph. Boom. Next, we're going to do 3 transformations on the graph of y equals the cubed root of x. So we'll start with the cubed root. And it says shift left 2 units. That's a horizontal shift. So that's going to be on the inside. So step 1 makes it go cubed root of x, and it's going to be on the inside. And it's left 2 units. So we're going to add 2. Horizontal stuff always goes opposite of what you would think. Because now, originally it would be 0, 0. Now we have to go to -2 to get it right where it needs to go. Next, we have the second transformation, reflect across the x-axis. So I always flip these, I always mess these ones up, and I always have to remember it in my head. So if we're reflecting across the x-axis, our x-coordinate will stay the same, but our y-coordinate will change. That means that it's a vertical thing, should happen on the outside based on our pro tip. So this will be negative on the outside, cube root of x plus 2. Last but not least, we're going to vertically stretch by a factor of 4. That's a vertical thing. It happens on the outside, and that means you're multiplying by a factor of 4. So that would be, in the third transformation, that would be 4 times our function, negative cube root of x plus 2, or preferably y equals negative 4 times the cubed root of x plus 2. So the cubed root function, if you remember your parent graphs, has the point 0, 0, 1, 1, and -1 comma -1, and it looks roughly like that. And so, utilizing this, we're going to take our important points that we have, and you also have the point 8, comma 2 and -8, comma 2 if you want to plot more points. But so 1, 1. First, it gets shifted left 2 units, 1, 2. Then it gets reflected across the x-axis. So it's up here, now it's down here. And then it gets vertically stretched. So we're going to quadruple the x-coordinate, quadruple the y-coordinate. 1, 2, oopsies. It goes from -1, quadrupling a y-coordinate of -1 would be -4. And so I forgot about that on this one. So there is 4. And there is -4. Sorry about that. So once again, so let's start over. So we have the point 1, comma 1. We're going to shift it left 2 units, 1, 2, reflect it across the x-axis, boom. And now its y-coordinate is -1. So if we stretch that by 4, we're going to like vertically stretch it. We're going to quadruple it. So -1 quadrupled would be -4. So right there at -1, comma -4. 0, 0 is the next point. Shift it left 2 units, boom, boom. Reflect it across the x-axis, it's on the x-axis. Vertically stretch it, its y-coordinate is 0. So quadrupling 0 is still 0. So you have the point -2, comma 0. And last but not least, we have the point -1, comma -1. Shift it 2 units to the left, 1, 2. And then vertically reflected across the x-axis. So it gets flipped up to here. And then quadrupling the y-coordinate would put us at 4. So you have the point -3, comma 4. And so now that we've got all those points, let's plot them. So 3, comma -3, comma +4 is right there. -2, 0 is right there. And then -1, comma 4 is right there. And so it will look roughly like that. Sorry about that. And that will be how we take transformations in and convert them. Now, the other thing that could happen is they give you a function and you need to figure out the transformations that happen. Full disclosure, I do this differently than the book because I feel like my method is easier to memorize, and it also makes it so that everything happens neatly. You'll see in a second. However, absolutely vital. if you're going to follow my method. If you like the method of the book, kudos to you. Feel free to continue. But if you want to follow mine, then this is what you do. Step 0. This is very, very important. If you don't do this step 0 with my method, it will not work. So step 0 is if there is a quote unquote a negative x, factor out a -1 on the inside. So for example, if they gave you y equals the square root of -x plus 2, that's the negative x that I'm talking about. And so what you're going to do is you're going to factor out a -1 on the inside. So you're going to go to y equals the square root of negative parentheses x minus 2, because by factoring out the -1, you change the sign of everything on the inside. Next, you're like, so as long as that's happened, if it's not there, if there's no negative x, skip step 0. Then step 1 is going to be follow the transformations in the following order. First, we take, so this is the first steps, and then the last steps are at the bottom. So first, you're going to take care of reflections. And the cool thing with my method is that it doesn't matter which reflection you do first. If there was both, so for example, if the curve was negative square root of -x, based on my method, it doesn't matter whether you do the reflect across the x-axis first on the outside or the y-axis on the inside first. That's the thing I love about this. So you take care of reflections first, then compressions and stretches, /stretches. And it doesn't matter if you do a vertical or a horizontal. We don't do any horizontal ones, but still, it wouldn't matter if you did the vertical compression or the horizontal compression first. And last, you do shifts. And once again, in this method, it doesn't matter if you do the vertical shift or the horizontal shift first. It really doesn't, because of how I set this up. And so this is the reason why I called them compressions instead of stretches, because I can teach, like, then we can have a little memorizing technique, RCS. RCS. And the mnemonic device is these transformations are some really cool stuff. Right, guys? Are really cool stuff. S. I know that's what you're all thinking. I can sense it through the through the ether here, that you're like, man, this is the coolest stuff ever. This is really cool stuff. The original joke I had was, if you like Pokemon, they'd say Arceus, the god Pokemon, but apparently I was corrected on that it's pronounced Arceus. So it doesn't fit exactly as well, but I still want to call it Arceus. But anyways, that's how I memorize it, is really cool stuff, RCS. The last step, step 2, is to use your reference, like use a reference parent graph along with your work to graph. So you're going to use the reference, use a parent graph for reference to figure it out. So let's look at some examples. Given the function g of x is equal to 3 times the absolute value of x plus 1 minus 2, identify the parent function and the transformations necessary in order to arrive at g. Then graph g. Okay, so the parent function is the function that would be there if you got rid of all the numbers. So if I were to kind of scratch that out and that out and that out, all I'm left with is the absolute value of x. So that is my parent function. The parent function is f of x equals the absolute value of x. So we could draw the graph of it first if we wanted to, but I'm gonna work on this first. So for g, there's no quote unquote negative x, so we're gonna skip step 0 and just move on to R, C, and S. Reflections, those are going to be negative signs on the inside or the outside, which there are none. There's no negative sign here. There's no negative sign here. So none. There's no reflections. Compressions or stretches, there is one. There's a vertical stretch by a factor of 3. So vert stretch by 3. And there's no horizontal one, even if like we don't go over them, but even if we did, there are none here. And then we talk about shifts. So it doesn't matter if you do the vertical shift or the horizontal shift, as long as you follow my method, to be clear. It doesn't matter which one you do first. So I'm going to just look at it. The +1, that is going to the left one because it's a +1, which I would think would make me go right, but remember that horizontal stuff is counterintuitive. So it's left 1 and then down 2 because that -2 on the outside. So our parent graph has the point 0, 0, 1, 1, and -1, comma, +1. And is those rays going out of it, making a V shape like that. And so now all we need to do to graph it is just follow this from top to bottom with our points. So we have the point 0, 1, comma, 1. No reflections. Vertically stretch it by a factor of 3. That's going to be tripling the y-coordinate. The y-coordinate is 1, so triple of 1 is 3. So we're at 1, comma, 3 at the moment. Then we go left 1 and down 2 to the point 0, comma, 1. That's where this point goes. Next, 0, 0. No reflections. Vertically stretch it by a factor of 3. So we're tripling its y-coordinate, but its y-coordinate is 0. So it just fizzles. Then we shift it left 1 and down 2 to -1, comma, -2. Last but not least is the point -1, comma, +1. We're going to vertically stretch it by a factor of 3, so we're tripling it. So it's up here, because tripling a y-coordinate of 1, multiplying it by 3 would give you a y-coordinate of 3 now. Then left 1 unit and down 2 units to -2, comma, +1. And so now I can plot those values. So 0, comma, 1, -1, comma, -2 right there, and then -2, comma, +1 right there. And then we continue that V shape. And that's the graph of your function. You can also take the point 2, 2 and do the exact same thing if you've got more space on it. So like just for argument's sake, 2, 2, you would triple the y-coordinate. That would put you at 2, comma, 6. Left 1 unit to get you at 1, comma, 6, and then down 2 units to get you at 1, comma, 4, and so on and so forth. Next problem, given the function h of x is equal to 1, comma, 2, 1/2 square root of -x plus 3. So if we were to get rid of all the stuff except for the x, we'd have the square root function. So that's our parent graph, our parent function, wrong font, f of x equals the square root of x. And so there is a -x, has quote unquote -x. So we're going to convert it to h of x equals 1/2 square root of negative parenthesis x minus 3. Because we factored in a negative sign on the inside, so that's going to change the sign of everything involved. That's why it's now -3. Now that we've done that, we follow RCS, the really cool stuff. There is a reflection. It's on the inside of the function, so that's a horizontal reflection, which is a reflection across the y-axis. So reflect y-axis. Then for compressions or stretches, we're looking for any number multiplied into this thing, and there is one. It's less than 1, so it's a compression. So it's a vertical compression, vert compression, so comp by 1/2. And then there's no other one. There's no horizontal compression or stretch. And then we look for shifts. There's no adding or subtracting on the outside. So there's no vertical stretches or vertical shifts, but there is a -3 on the inside. And so -3 would make you think you're going backwards, but it's counterintuitive because it's the horizontal stuff. So we'd move 3 units to the right. So right 3. So our parent graph has the point 0, 0, 1, 1, and then 4, comma 2. And then we could also do 9, comma 3 if we had space for it, but I don't. So it looks roughly like that. And so let's transform all those 3 points. So starting with 0, 0, we're going to reflect it across the y-axis, but it is on the y-axis, so that fizzles. We're going to compress it by a factor of 1/2, so we're going to take its y-coordinate and halve it, but half of 0 is still 0, and then we're going to shift right 3, 1, 2, 3, to there at 3, comma 0, and we'll jot that point down, 3, comma 0. Next, we'll take the point 1, 1, we'll reflect it across the y-axis, so over to here. We'll vertically compress it by a factor of 1/2. So we're going to half its y coordinate. Half of 1 is 1/2. Then we're going to shift it right 3. So 1, 2, 3 to, that is 2, comma 1/2. Then we'll take the point 4, comma 2, which is right there. Sorry, it's not on the graph. We're going to reflect it across the y-axis to now negative 4, comma 2. Let's just kind of make this go out just a smidgen and say, right there is negative 4, just so we can see it. 4, comma 2, negative 4, comma 2. Then we're going to vertically compress it by a factor of 1/2. So we're going to half the y-coordinate. Half of 2 is 1. So now we're at negative 4, comma 1. And then we shift right 3 units. 1, 2, 3 to negative 1, comma 1. And then we could do the same thing with the point 9, comma 3 if we needed to, but I think 3 points should be enough. So 3, comma 0, 2, comma 1/2 is right there. And then negative 1, comma positive 1 is right there. And then we just fill out the rest of the graph. And that completes that problem. Oh, and I've been meaning to underline. No, I've been meaning to underline these things. I'm so sorry. Just want that. Didn't do it here as well. Phil, is that really necessary? Maybe. If you want to just skip like 10 seconds in the video, go right ahead. But it's bugging me. Come on. All right. So this last one is kind of a conceptual problem where we're given a parent function that's not one of our normal library of functions. It's this kind of little weird cup shape, like a slanted cup or whatever, if you wanted to connect it here. I don't know. So the graph is given below, and we're going to graph the function y equals negative f of x plus 1 minus 2. So it's telling us all the transformations here. There's no quote unquote negative x, so we'll skip step 0. If the like it would look like this if we were talking about, it'd be like f of negative x plus 1 if we wanted to talk about a reflection across the y-axis. And then you transform it to f of negative x minus 1 if you wanted to do that, like if that was the problem. But either way, it's not like that. The minus sign is on the outside. So since there's no negative x on the inside, we skip step 0 and then follow really cool stuff, RCS. Is there a reflection? Is there a minus sign being multiplied or next to an x? Yes, there is. It's on the outside, meaning it's affecting the y coordinates. So it's a reflection across the x-axis. Reflect x-axis. Compressions or stretches, that would be a number being multiplied into the function or into the x, which there isn't. So none. But there are 2 shifts. Anything that's added, this is being subtracted or subtracted. Subtracted on the outside, so we're going to go down 2. And then we're adding 1 on the inside, so we're going to be shifting left 1. And once again, with my method, it doesn't matter which you do first, horizontal or vertical, as long as you follow my method. But if you like the book's method, that's your choice. So let's start off with, we'll follow what happens to each point. Negative 3, comma 1, right there. So first, it gets reflected across the x-axis. Whoop. to now to 3, negative 3 comma negative 1. Then it goes down 2, 1, 2, and then left 1 to the point negative 4 comma negative 3. I know it's kind of a little weird situation because this is the first time I haven't made each 2 tick marks one, but this one, let's just make sure we make that argument. So negative 4 comma negative 3. Next, we will do the point negative 1 comma negative 3. Negative 1 comma negative 3. First, it gets reflected across the x-axis, so it gets shifted all the way up to 1 comma positive 3. Then it gets down 2, 1, 2, and then to the left 1 to the point negative 2 comma positive 1. Then the point 2 comma negative 3, so 2 comma negative 3, reflect across the x-axis, so whoop to there, down 2, 1, 2, and then left 1 to the point 1 comma 1. And yes, the whoop sound is definitely necessary when you reflect. Last but not least is the point 3 comma 4 right there. 3 comma 1, 2, 3, 4. We're going to reflect it across the x-axis, so whoop down to 3 comma negative 4, down 2, 1, 2, left 1 to the point 2 comma negative 6. Now that we've got all of our points, we'll start to plot them. So negative 4 comma positive, sorry, negative 4 comma negative 3 is right there. Then negative 2 comma positive 1 is right there. 1 comma 1 is there. And then 2 comma 6, negative 6 is right there. And then we just graph it. Like that. And we're all done. And that will complete it for this video. And I will, oh, and then there's a challenge problem here. It's a very, very clever problem. I hope you guys like it. The key thing is to know what happens to your X and Y coordinates when you do transformations. So I got the answer there. If you have questions about it, feel free to email me, and I'll see you guys on the next one. See ya.